Okay, so uh, hello everyone, and this is the okay. So welcome to this fourth class on electromagnetic theory, and this is a TA course. Yeah, I'm doing it as a part of my PMRF TA-ship. So I'm currently doing my PhD here at IISc, and um, today we'll be talking about electromagnetic theory. Now, from in the last three classes, what we had discussed was we started with electrostatics. So we started with Coulomb's law. Then we moved towards Gauss's law, which made use of the symmetry that is there in the systems. And we saw that in many cases where there is proper symmetry, we can actually make use of Gauss's law, and the field or the potential calculations can become quite easier with Gauss's law. And we also got the differential form and the integral form of Gauss's law and all that. So all the relations between charge densities and electric field and potential, we discussed about all that. And then we moved towards, in the last class, what we did was about conductors. So while there can be dielectrics where there is some net field inside the material when you keep it in presence of some external field, but for conductors the net field inside the conductors goes to zero, and we saw how this charge induction that happens. Okay, so the concept of induced charges was discussed, and from there we got to see how this field gets cancelled and what are the different properties of a conductor, how useful they can be. Okay, and what is the relation between the medium properties, okay, the polarization of a medium, how does it get related to the applied field, the concept of susceptibility and all that. Okay, so what we will do today is we'll start with Laplace equation. So basically in the I think second class where we started with Gauss's law and we went to the differential form, we got to this Poisson equation which relates charge density with the potential. Okay. So you remember we got to this from the relation that divergence of E is equal to rho by epsilon naught. And then you can write the electric field as a gradient of some potential V. And then you got to this relation, right? Now, what happens when this rho, that is volume charge density, when that goes to zero? So if that goes to zero, we get del square V equal to zero. And this is our Laplace equation. So in today's class, we'll mostly focus on how to solve this Laplace equation. Okay, based on the different boundary conditions, we can go from 2D to 3D, 1D to D, 3D, all that kind of questions. Okay, and we can go from rectangular coordinates to spherical coordinates. Okay, so we will discuss all such different kinds of examples of solving Laplace equation and see how one can get an idea about the potential, about the charge densities, okay, surface charge densities, so all of that. And then we would move towards the method of images, okay, so which also comes as a consequence of some properties of Laplace equation. Okay, so let's gradually proceed towards it and it will be clearer as we discuss. Okay, now there are certain properties of functions which are solutions to this equation. So if you have del square V equal to 0, and then you find a V which satisfies this condition, this V is basically an average of its surrounding. So in 1D, it will be something like this. So in 1D, if you take a point at, like you want to find Vx at certain point X, it's basically an average of what you have just before and after. Okay, so Vx plus A and Vx minus A, and if you do an average of it, that is what Vx is. Okay, so Laplace equation is a kind of averaging. So what it means is, suppose if you talk about two dimension, so it would be something like this. So if you have a potential, so suppose you want to find a potential at a point, at some given point, somewhere here. So what this is telling you is that if this region satisfies this condition, that is, the Laplace condition is satisfied and you want to find the V at this point, then what it is telling you is that if you draw a circle some curve, like for simplicity, let us consider a circle. So if you draw a circle, and then if you know the potential at all of these points along the circle, okay, so you do a line integral v dl along the circle, along the circumference of the circle, and then divide by 2 pi r. So basically now you are doing an average value of all the potential that is there on the surface of this circle enclosing the point, right? And that will actually be the field that you have at this point, right? Similarly, for 3 dimension, what it means is, now if you consider a point like this, the same point, but now you consider a sphere around it. Okay, so suppose you want to find the potential here. So you find a sphere around it, and then you do a, like, there is a surface enclosing this point. Okay, that is the surface of the sphere. So if you do a surface integral over this entire surface of the sphere and divide by 4 pi r squared, which is the surface area, you're basically finding the average of all the points that are there on this surface, right? So you take all the points of potential on this surface, and then the average of that is equal to the potential that you have inside. So this is a very important and interesting, observation, because what it is telling you is that if you know the potential here, and if you know that this region satisfies Laplace relation, so there is no charge density in this region, and if you know the potential at a point, you basically have an idea about what the average of the potential is in this region surrounding the point. Okay, so if we want to look at a proof in 3 dimension, we can start with something like this. So here you can consider some charge q, okay, and there is this sphere. So there is no charge inside. Okay, so this region satisfies the Laplace equation. Here rho is 0. Inside this, okay, let me change to the pointer. So inside this region, rho is 0. And because rho is 0, here Laplace equation holds. Now, suppose there was some charge q here, right? Now, because of this charge q, you would have a potential along the surface, right? It's expected. So what is that potential? So you can do an integral like this. So you can take multiple points and get an estimate of the distance from charge q to this individual points on the surface of the sphere, and then do an integration, right? So this is the average of the potentials all along the surface of this sphere. And what do you get? You get 1 by 4 pi epsilon 0 q by z. Now, what is this? This is same as finding the potential at this center here, right? If the distance from q to this point is r, then you can just write the potential here would be given as 1 by 4 pi epsilon 0 q by, like, that particular distance, right? So that means the average is precisely the potential due to q at the center of the sphere. So this is what we mean. So by the superposition principle, the same goes for any collection of charges. Okay. So that means the average potential over a sphere is equal to the net potential they produce at the center. Okay. Whenever you have your Laplace equation that is satisfied. So the solutions of Laplace equation is a average of the potentials that are around it. Okay. Now, because it's an average, what it also means is that Laplace equation tolerates no local maxima or minima. Okay. So that means what it means is, so suppose if you say that the potential here is actually an average of all the potential you have here, so this cannot be a maxima or a minima, right? If it is a maxima or a minima, it is not an average, right? So whatever maxima or minima might be present has to be present on the surface, not inside the volume. Okay. So if there were a local maximum, then V at that point would be greater than on either side, right? And therefore could not be an average. So that means, and same goes for the minimum. So that means Laplace equation requires that, the second derivative, it seems reasonable that solutions should exhibit no extrema. Okay. However, this is not a proof since there exists solutions. So in general, you can just say that, just by del square V going to 0 is mathematically not sufficient to tell that, there is no, like, maxima or minima. There can be maxima or minima, but what the Laplace equation requires is that because it's an average of what you have around, at this point, inside the volume where the Laplace equation holds, there it has no maxima or minima. Okay, it's an average value. So whatever maxima or minima has to be there on the surface enclosing the volume. It has to be outside. Okay. So now, based on what we just discussed, let us try to solve for the Laplace equation. So we start with a two-dimensional problem. Okay. So two infinite grounded metal plates. So you have these two plates, and both of them are at potential 0. Okay. And there is this, conducting like infinite strip here, which is isolated from this two plates. And here it is at a constant potential V. Okay. Now what it is asked is find the potential inside this slot. Basically, you have to find the potential here, all throughout this region between these two plates. Now, in this region between the two plates, there are no charges. So that means rho is 0. So that means the potential here does satisfy Laplace equation. And because the problem does not depend on z, there is no z dependence here. So you can just write it in two dimension. So we have to solve the two-dimensional Laplace equation, which is given by this relation here, right? So we want to find V. So for this, first we have to look at what are the boundary conditions. Okay. So like here, what are the things that are given? So it says that V is equal to 0 when y is 0. V is equal to again 0 when y is a. Why? Because these two plates are at 0 potential. That is given. Now, at x equal to 0, that is here at this point, we saw that V is equal to V naught y. Right? So that's a constant potential. That is also given. And obviously very far from this point. So if x tends to infinity, if you go very far from this point, then the effect will be negligible. So V tends to 0 as x tends to infinity. So these are our boundary conditions. So based on this, we have to solve this relation, right? So how do we do it? So the first step is to look for solutions in the form of products. So let us start with this idea. So basically we want to find V. So we start with something, and then we see that what are the different conditions that has to be imposed on that solution, so that these boundary conditions are satisfied, right? So to start with, we take a form of V, where V is given as product of these two functions. One is x, which is a function of only x, and y, which is function of only y. Okay. Now, if you use this form and put it here, right? So you would get a form like this. This is just partial derivatives. Now, the next step is what is called separation of variables. So we want these two terms to be like solely of either x or either y. So that's why what do? We divide by xy. Okay. So that means this term becomes independent of y. This term becomes independent of x. So this is only a function of x, only a function of y. So it's of the form fx plus gy equal to 0. Now for this condition to hold always, irrespective of the value of x or y, we want this relation to always hold, right? This is the condition of Laplace equation. So it will always hold for whatever value of x and y. So that tells us that these two constants, like these two functions, has to be constants. Why? Because if it was not a constant, it was some random function of x, and this is some random function of y, then if you keep one constant and vary the other, the equality to 0 will not be maintained, right? So for this relation to always hold for all whatever value of x and y, this two has to be constants, and the constants should be related to each other. How? By this relation. So if you take one of them to be C1, another to be C2, then C1 plus C2 should go to 0. So that means one has to be a positive, another has to be the negative of that, right? Now at this point, we take up a form of the constant as k square. Why are we taking it will be clear in some time, because this makes this is for mathematical simplicity. We would see that this will make our mathematical form easier and more meaningful. So that's why we would take a constant like this. Okay. So del square x del x square is equal to k square x, and del square by del y square equal to minus k square y. Now, here you can ask, how do we know which one is positive and which one is negative? Because here we have chosen C1 to be positive and C2 to be minus k square, right? But how do we choose? We could have chosen the opposite one, right? So there, what we have to make use of is the boundary condition, right? Why? Because here you can see that the potential goes to 0 at y equal to 0 as well as at y equal to a. So there has to be, how do I say? So if we have a form like this, if the differential equation has a form like this, we would have sinusoids and cosines coming into picture, and then that would be useful because we would be then able to establish this boundary condition. Similarly here, okay, so currently we are trying to look at solutions of Laplace equation in 2 dimensions. Okay, and we are starting with this very idea of separation of variables. Are you acquainted with it, or like should I start from the beginning? Okay, so I'll consider that it's okay. So basically what we are trying to do is we know certain boundary conditions that are given, and we want to solve the Laplace equation because we want to find the potential in this region where there is no free charge. So rho is 0 here. So we want to find V. So these are the boundary conditions. We take up a form of, potential, which is basically product of 2 functions. Of one is a function of x, another is a function of y. Then we apply the idea of separation of variables, which takes up a form like this. Now, for this to hold for all values of x and y, each of them has to be individually constants. And because of that, we consider like one to be C1, another to be C2. So C1 plus C2 should go to 0. Now this constant, we take up a form of k squared. Why k squared? Because of the mathematical simplicity that it will bring into our solution. Okay. Whether which one to choose, like out of x and y, which one like will have the constant corresponding to a positive value and which one will have minus k square, depends on the boundary condition. So here you can see, so if you have a k square, if you look at this relation, this will give you an exponential form, something like this. While if you have minus k square, you would have a form which would involve sine and cosines, right? So whether you want this form in x or you want this form in y depends on the boundary conditions. Here you can see that the potential goes to 0 at y equal to 0 as well as y equal to a, which makes us believe that if we have a form of sine and cosine in the function y, it would make our, like it would be more meaningful, then we would be able to apply the boundary conditions properly. Similarly here, as you can see, as x tends to infinity, this goes to 0. So if you have an exponential form, you can actually play with it. So what it means now is that you get an expression of x, which is like only a function of x, and then you have something which is only a function of y. So now v of xy based on this relation will have a general form like this. Okay. So what we have to do next is we have to apply this boundary conditions to this general form. Okay. So suppose if we start with the fourth relation, which is already telling you is that as v tends to 0, x tends to infinity, v tends to 0, which means you cannot have this exponentially increasing term, right? So that means a should go to 0. So that already gives you a form of potential which is more simplified. Then you get a form like this, right? Now let us do the next. So here we apply condition 1. What is the condition 1? That is v equal to 0 at y equal to 0. So if v has to be 0 at y equal to 0, we cannot have the cosine term because cos 0 is 1. So you would have a non-zero value, right? So this d has to be removed. So d is 0. So that gives you an even more simpler expression of potential, right? So now if you apply, this relation v equal to 0 where y equal to a, so what are the typical relations which satisfy this condition? So any value like we want sine k to be 0, and that can be possible for all values of k given as n pi by a, right? So basically, for n equal to 1, 2, 3, infinite number of values, all these values of k will give you individual values of potential like this expression, and all of them will satisfy the condition, right? But one condition is still left. The third condition we haven't applied yet, right? We have applied the first three, like 1, 2, and fourth condition, and that has led us to this relation. Now, because Laplace equation is linear, that means all the solutions of Laplace equation, so if we do a superposition of all of them, that will also be a solution, right? So we consider a more general form where we say that now we take up all the possible values with n running from 1 to infinity, and you have this Cn e to the power. So in place of k, you replace it by n pi by a, and then you do sine n pi y by a. So all these individually are solutions to the equation, and you take the most general form where you take a superposition of all of them. Okay. Now you apply the third condition, right, which says that at x equal to 0, v should be v naught, which is some function of y, some value here, right? So that means now if you put x equal to 0, okay, so you get this form, then this summation, this entire solution should be equal to v naught of y, right? So here we make use of this Fourier trick, which is basically working on this idea of orthogonality of functions, okay? So the orthogonality relation tells us that if you have two sinusoids, okay, like sine n pi y by a into sine n prime pi y by a, so from 0 to a, so if you have a form like this is telling you that when n prime is equal to n, only then we would have a non-zero value. So that's an orthogonality condition. That means for all other n prime values, they're orthogonal to each other, so the relation turns out to be 0, right? So we use this orthogonality relation, and what we do is now we basically multiply both sides by sine n prime pi y by a and do an integration. Okay. So this side, the left hand side simplifies itself because you just end up getting a by 2, and so you can actually find the coefficients from here. So that means now if this was your more general form of your potential, now you know Cn, that are the coefficients, right? So now if you put the coefficients, so if you now put the coefficients, okay, so if you simplify it further, you would see that for this question, all like whenever n is even, this is going to 0. All for the other odd values, you get a simplified form of your coefficient. So now you put this value of the coefficient in equation, 3.30. Basically, you are writing the expression for the potential. So this is your expression of potential. Okay. So in all these kinds of question, like later we will talk, when we talk about spherical coordinates, we would again use this orthogonality, but there we would bring in new orthogonality conditions because the functions will be different. But for this method to work, we have to have a set of functions which are orthogonal and complete. What do you mean by complete? Complete means that any function, some function fy, can be written as a combination of these functions, because that is the relation that you have used here, right? You had got some conditions, some solutions, and you say that any solution can be written as a combination of these solutions. So here, because sinusoidal functions like these functions, they are orthogonal to each other and complete, that's why we are able to use this technique. Okay. So that's how you solve for the Laplace equation. So here, this is your simplified, like this is your expression of potential. Okay. Now, suppose now we want to determine the charge density on the strip at x equal to 0, assuming it is a conductor or at constant potential V naught, right? So that means, now this is your form. Basically, what it is telling you is, initially you had this function, right, which is a function of y. If this is a constant quantity, if it is a constant potential, then your expression gets simplified. So you get an expression like this, okay, where V naught is a constant quantity. So that means in this question, it is said that V naught now is some constant value. Fine. The next question is, so if this is at a constant potential, and now if we want to find what is the charge density, the surface charge density in this strip here, how do we find that? Okay, so that's the question. So this is your expression of potential. Okay, so we use this relation sigma is equal to minus epsilon naught del V del N. Okay, so this actually gives you the charge density on the strip at x equal to 0. Okay, so any idea how we got to this form? Like why, how do we get to this relation? Any idea, guys? So we know the potential. We know the expression of potential inside. We know the potential expression here. We know that this is at a constant potential. The question is asking, what is the surface charge density on this strip? And this gives us a relation of surface charge density on the strip. But how do we get to this relation? Any idea? You can also write in the chat box if you want to. So see, okay. So basically what it is telling us is that we have a region, we know the potential here. So this is your potential xy, which you find from making use of your Laplace relation, right? And then you have some, surface here, some surface, consider it to be some infinite strip, which is at a constant potential V naught. Okay. You want to find the surface charge here, sigma. So here we use the relation that, okay, so I know the potential here. I know this is at a constant potential. This surface is at a constant potential. We want to find the charge density. So we know that if we know the potential, we also know electric field, right? And for a surface, if you remember the boundary conditions that we had discussed before, if a surface has a charge sigma, okay, we know that the normal components of the electric field are discontinuous, while the tangential components to the surface, so this parallel components will be equal below and above the surface, while the normal component, like E above minus E below, will have a discontinuity, right? And from there we could write that basically E is nothing but sigma by epsilon naught n cap. N cap is your normal vector, normal to the surface, right? And E is nothing but minus grad V, right? So now if you know V, you know E. Once you know E, you can actually use this relation to find sigma. And that is what is being done here, right? So del V del N is nothing but grad V, okay? So you're using basically this relation. Is it clear? So whenever you know the potential in a region, okay, so and then you are asked that, okay, there is this surface, we want to find the charge, the surface charge there, you have to use this relation. And that comes from this. So either you find electric field and then use this relation or directly use this relation, okay? So that means for this question, you know the potential. So now you do a derivative with respect to x and then minus into minus epsilon naught. So that gives you the value of sigma, which is your charge density. Okay. Now, there can also be questions like this. So here it's the similar kind of question, but now the boundary conditions have slightly changed. Okay, sorry. So initially you had from 0 to some distance, now your box ranges from minus b to b. So basically you have an added symmetry in x. Okay. And then again, the v goes like v is equal to 0 at y equal to 0 and at y equal to a. Okay. And then you have these two constant potentials at x equal to b and x equal to minus b, which means your whatever expression of potential you find, that has to be symmetric about x, right? Because your condition, as you can see here, it's symmetric about x. Okay. So now you want to find the potential inside this rectangular pipe. So whatever you have is outside, right? Inside this point, there is no charge, no rho. So that means again Laplace equation. So you want to find v. So what do? Again, we write del square v del x square plus del square v del y square is equal to 0. What are the boundary conditions? So v goes to 0 at y equal to 0 and a. V is equal to v naught at x equal to b and minus b. Okay. So we can start with this general form of v and then keep applying the boundary conditions. Okay. So again, as you can see, you have here x, like the potential is symmetric about x. So that means this function should be symmetric about x, right? So that already tells you that a and b should be equal, right? So here, as you can see, so it is symmetric about x. So that means a should be equal to b. So you can simplify this relation, like this part, to something like this. Now, what is the other condition? So again, here you have v going to 0 at y equal to 0 and y equal to a. Okay. So that means d should be 0. Why? Because if d is not 0, you cannot have v equal to 0 at y equal to 0. Cos 0 will be 1. So this will be a non-zero quantity. So d should go to 0. What should be the condition of k? Again, k should be equal to n pi by a, so that at y equal to a, your v goes to 0. Okay. So that means now this is your general form of potential. All such combinations of functions for different values of n will satisfy this condition, whatever condition you have here. So now you do a linear combination of all such functions. So this is the general form of your potential. Here you apply the condition that at x equal to b, v is v naught. Okay. So you put x equal to b, and so this entire summation, this entire relation should go to v naught. Okay. Now again, what you have to do is you have to use the Fourier trick. So multiply both sides by sine n prime pi y by a. Okay. So again, you would have so basically the same technique. Okay. This relation. Just like here, you can see you have multiplied both sides by sine n prime pi y by a and have done an integration from 0 to a. And this relation has been used. That's the orthogonality condition, right? So the same thing will be used again here. So this is the relation that you would end up getting. So that means now you can again write the expression of the potential, basically put the value of Cn like this term here in the general most expression, and this is the relation that you get. So in this way, you can actually try to find potential for different kinds of problems based on different boundary conditions that you have. Okay. Now, there can also be conditions like this, where, this is another kind of boundary condition. And then you have to find the potential inside the pipe. Now here, as you can see, you have a relation along x, along y, and along z, right? So it becomes a three-dimensional problem. Okay. So again, how do you do? These are your boundary conditions as given in the question. So whenever you have to solve this kind of problem, try to see what is the dimension that is involved in the question and try to jot down the boundary conditions that are given. Okay. Now you have to have an expression of v, and this has to be in 3 dimensions now, right? So you would have basically three constants involved. Initially in 2 dimensions, you had 2 constants. One was k square, another was minus k square, right? But here you would have 3 constants because you have 3 variables, right? X, Y, and Z. So basically you have to take v as a function of x, y, and z, and then use the separation of variables, take each of them to be constants. So C1 plus C2 plus C3 now should go to 0. So here, this is how you choose your constants. Why? Again, you have to make use of the boundary condition in choosing the form of your constants. Okay. So here you can see that, this x tends to infinity, v tends to 0. So you can say that for x, we can have an exponential form and work with it, right? So this relation gives you an exponential result. So you can have this constant k square plus l square associated with x. And if this is k square and l square, obviously one of them has to be minus k square, another has to be minus l square, right? So that's how you divide your constants and try to solve for your individual, differential equations. So this is what you end up getting. So now the most general form would be to multiply all the three and then start applying the boundary condition, same as we did for the two-dimensional case. So using this boundary condition, again, if you apply, okay, this is what you will end up getting. So again, a will go to 0 because so that v tends to 0 at x tends to infinity. Again, d will be 0 because at v equal to 0, y is 0. F will be 0. Why? Because at v equal to 0, z is 0, right? And then these are like, you have this condition, v equal to 0 at y equal to a, v equal to 0 at z equal to b, which tells us the values of k and l that is possible. So this is your form of your solutions. Now you take all such combinations. So now you have two variables, right? N and m, because you have x and y and z both. So now you take a linear superposition and then apply this condition that at x equal to 0, v is v naught. Okay, so all this combination together should give you v naught. And here you have two sinusoidals involved, right? So you can use the orthogonality condition twice. Okay, so you can use two orthogonality conditions, as you can see here. One is for the y variable, another for the z variable. Okay, and then from there write an expression of the coefficients. Once you have the coefficients, basically you have the potential. So this is your expression of potential. So if you have a constant potential, you can simplify your problems further. Otherwise, based on the form of your V naught, your coefficients will change. So once you get the coefficient, now you just put in the final expression. So this is your expression of potential. So you have to practice this, solving for this differential equations and solving for Laplace equations and get used to how, you have to choose the boundary conditions, the constants, and the orthogonality relations. Now, suppose, like in the last case, we saw for the general case, some V naught, which is function of y, but you can be given certain, specific functions. Like here, the same problem, it is said that, the V naught, the potential is V naught from 0 to a by 2, and then minus V naught from minus a by 2 to a, right? So that means now you have to use this specific form of potential, okay? So what this is telling you is, this was the general form, what we had discussed previously. Now, in the question, this V naught of y is actually given to you, right? So it is given that from 0 to a by 2, it is V naught. From a by 2 to a, it is minus V naught. So you have to put it here to find the coefficients. This is how your, it can change from question to question, okay? So now if you put in here, you have to then just solve for the coefficient. These are typical integrations that one has to do. But important is to remember how we are bringing in the boundary conditions. Okay, so then this is the form of your potential, coefficients that you get. So based on this, your final expression of potential will change because now the coefficient has changed. Okay, so this is the expression of potential, which basically you put in the value of the coefficient in the general expression of potential. Okay. Now, you can also do the same for, spherical coordinates, where basically now you have to write the Laplace equation, but in the spherical coordinate system. Okay. So this is the typical expression of Laplace equation, del square V in the spherical coordinates. One can consider azimuthal symmetry. So then this last term goes away. So this is again some differential equation where the first term is a function, is just involves derivative with respect to r. This only has derivatives with respect to theta. So you can again take a solution of a form where you have this product of r, which is just a function of r, and theta, which is just a function of theta, and then use the relations. Basically, again, do the same, but for the spherical coordinates. So now this is just a function of r, this is just a function of theta. So for this to hold individually, this has to be a constant, this has to be minus of that, right? So you can now independently solve for r from here, and you can solve for theta from here. So if you do that, this is the general form of r, and this is your general form of theta. So these are called Legendre polynomials. And again, this Legendre polynomials form a set of complete and orthogonal functions. Okay, so that means again, you can actually use the orthogonality relations, but now the orthogonality relation will be that of Legendre polynomials. Okay, how the Legendre polynomial looks is based, like you can write the expressions of the Legendre polynomials for different values of L by using the Rodrigues formula. Okay, so that means this is your theta, this is your r, so this is your general form of potential. Okay, so now if it is said that, the potential V naught is specified on the surface of a hollow sphere, find the potential inside the sphere. Okay, so how do you do it? So here, whenever it is asked to find the potential in case of spherical coordinates where you have the potential of this form, you have to see which are the, like, based on the region that is involved, you have to choose the form. Like here, when it says that what is the potential inside the sphere, okay, so you can see that if inside the sphere your r can take a value of 0, right, and if r takes a value of 0, this terms blow up. So that means in the general form of potential, you cannot have BL. Okay, so when you're talking about potential inside a sphere, you will just have AL terms, not the BL ones, right? So that means your general form would be something like this. Okay, so this is how you start with. Now what do we do? So we know that at r equal to r, so putting r equal to r, we know that the potential is V naught. So again, what do we do now? We use the orthogonality relation of Legendre polynomials. So we multiply both sides by PL prime cos theta. Basically this, right? And this is the boundary, the orthogonality relation. So that gives us the value of the exponent AL. Okay, so once we know AL, we basically know the expression of your potential. Okay, so let us look at an example. So if you have a potential like this, okay, so this is the potential on the surface of a hollow sphere of radius r, suppose. Okay, so we want to find the potential inside the sphere. How to do, right? So one way would be that you know the potential, and then you have to look at, so basically you know how the potential is on the surface. In closing, you want to find some potential inside. So basically you need to find a solution of Laplace equation, right? You can put in all the boundary conditions, but if you know this is in spherical coordinates and this is how the general form should be, so we can actually directly start by comparing the potential with this form. Okay, so what do? We basically rewrite this. Okay, rewrite the potential. So this is where this ideas of trigonometry comes in. Okay, the very formulas come in. So we rewrite this expression of potential in this form. Okay, so the first term is nothing but P naught cos theta. P0 is 1, okay, and P1 is cos theta. P1 of cos theta is cos theta. So basically now you are writing your potential in terms of the Legendre polynomials. Basically now you can compare this with this form, right? So if you compare this to, what will you get? You will get the values of AL, right? So here, if you compare this with this, you can write a value of A0 and A1. So only A0 and A1 remains. All other terms are 0. Why? Because as you can see here, only L equal to 0 and L equal to 1 is there in the potential, right? All other terms are not there. So only A0 and A1 will be there. All other terms are 0. So now by comparing this with this form, so this is the potential at the surface. That is, this is the potential at small r equal to capital R. So you compare this with this form and find the coefficients. So once you know the coefficients, then you can use this relation to find the general expression of potential somewhere inside. Okay, so you can see without doing actually any integration as of like, we can just directly look at the form of the potential on the surface and try to find the potential inside without doing any specific integration because we know these relations. Is it clear? So always don't just try to, try doing integrations or go like, you have to know the concepts inside, but once you know the concept, see where you can apply it. So here, just by looking at it, you should start thinking how to use the form of, Legendre polynomials in this, in the given potential form, so that you can find the coefficients. Okay. Now, suppose if it was asked, what is the potential outside? So if the potential has to be found outside, that means now your R can take any value of like greater than capital R to infinity, right? So there, that means if R goes to infinity, this term will blow up. So that means now in the more general form that you started with, this term cannot be there. So only these terms will be present. Okay. Because if you have R tends to R going to infinity, this will blow up. So this is not there. So that means if you are asked to find potential outside, you have to start with this form of potential. Okay. And then apply the boundary condition, do the orthogonality relations to find the coefficients. Okay, this is similar, the steps are similar, but this is what you have to understand. Okay, where to take which form of the potentials. Okay, so till now what we have discussed is that if you have a region where the Laplace equation is satisfied, then you can actually start with, this relation, use the separation of variables and try to find the potential. Once you find the potential, you can actually find the electric field by using this relation. Okay. And you can use this relation to also find surface charge density. Okay. Now, all different kinds of questions can come up based on the different boundary conditions that you have. So in the last year's assignment, this is a kind of question that I had seen. So here it is said that you have two conducting plates at z equal to -2 and at z equal to 2, maintained at two different potentials. Assuming that the plates are separated by a dielectric constant is given. The question is, find the expression of potential and then use the expression of potential to find charge densities. Right? So what do we do here? Right? How to start with the question? Do you guys have any idea? Like based on all that we have discussed, what should be our starting point for the question? Any idea, guys? Think, what are the boundary conditions that are given? What is the like, you have to always look for which dimensions are we talking about, whether it's a one-dimensional problem, two-dimensional problem, or three-dimensional problem, right? So see, basically here you are not given any condition about x or y, right? So it's a one-dimensional problem where you know the potential at two points, basically. Like you know the potential, like you have two plates, one at z equal to 2, another is at z equal to -2. You want to find what is the potential here, right? Somewhere inside. So now if you have to use the Laplace equation, we can start with using the one-dimensional Laplace equation. What is the one-dimensional Laplace equation? Del square V equal to 0. Now, if we have to write it in terms of Z, it will be del square V del Z square equal to 0. Right? Del square V del Z square equal to 0. So this is your boundary, this is your relation. What are the boundary conditions? So you have two boundary conditions. V is 0 at Z equal to -2 and V is 0 at Z equal to 2. Right? So first you have to find a relation of V. So that means you have to do derivative like integrations twice, right? From here you can write del V del Z is equal to A Z plus B kind of form. Like basically del V del Z is equal to some constant and then again do a integration. So you have a V which is a form of something like A, some constant A into Z plus B. So you have two unknowns, right? This is your potential. This is your form of potential. You have two unknowns and you have two conditions given. So if you use this condition to find the potential, you can actually try to find an expression for A and B, right? So once you know the expression of A and B, you know the value of Z for different values of value of V for different values of Z, right? Now, once you know the value of V, basically you can again use this value to find electric field or charge densities. How? So charge densities, you have to use this relation where this is nothing but, sigma is equal to minus. So here, normally it is epsilon naught, right? According to what we had discussed. So here, when it comes about, the dielectric constant is given, so you can put it as minus epsilon. And then basically, sigma by epsilon naught will be your electric field. So you have the expression of, so if you know the potential, you have to find del V del Z, right? So del V del Z, whatever is del V del Z, that into the dielectric constant will give you an expression of charge density, right? So this is a one-dimensional Laplace equation, which is much simpler than the ones that we have been discussing. Okay, so use the one-dimensional Laplace equation to find an expression of potential V, which is of the form of Az plus B. So basically use these two conditions to find A and B. Once you know the form of potential, you know everything, right? You know V, so you can find E, you can also find the charge densities, right? So that's how you have to answer this kind of questions. Is it clear? So I'll consider it's clear. Now, there can also be questions like this. This was another question from the last year's assignment. Okay. So where it says that, this is your V in free space, and there are the equations of equipotential surface for V equal to 0 and 30 respectively are. So the first part of the question is like very trivial. Basically, you know the general form. So now you set this to 0. Okay. So you get an equation, right? So the first equation will be setting this relation to 0. So 20x square yz minus 10z square equal to 0. So that gives you a general form of the potential for this surface, right? And similarly, if you equate 20x square yz minus 10z square equal to 30, that will give you the equation for the other surface. So just by equating this relation, okay, equating this relation to one time to 0, another time to 30, you can basically try to find the expressions for the individual equipotential surfaces. So that's a very straightforward question. Now, once you know the expression of potentials on the two surfaces, you can be asked what is the potential, general expression of potential somewhere inside. Okay. Or, so this is your general expression of potential which is given. So can you find electric field? Can you find the surface charge density? So you have two surfaces. One is at V equal to 0. Okay. So one is at 0, another is at 30, suppose. Okay. So you know that these are the two surfaces. You know the general form of potential. Okay. How do you find electric field? So electric field is nothing but minus grad V, right? So you know V, if you do a gradient of this, yes, gradient of this, you end up getting the electric field. So E is equal to minus grad V. So, so that means you have to do individual partial derivatives of with respect to X, Y, and Z, right? So you find Ex, Ey, Ez by doing a gradient of this expression of potential. That gives you the general expression of electric field. Now, once you know the electric field, the general expression of electric field, suppose you know, okay? So once you know the expression of electric field in general, you want to find what is the charge density maybe here on this surface, right? So what is the charge density on this surface? Or what is the charge density on this surface? So here you have to take care of based on this region, right? Like if you are given the point, so basically you will have a value of X, Y, Z specified. Okay. So suppose X, Y is specified. So based on this relations, whatever relation you get at the two surfaces, which are your equations of equipotential surface, you know the points where you have to find. So you know X, Y, and Z. Once you know X, Y, and Z, you know the exact, numerical form of your electric field. So once you know the numerical form, you can find the magnitude of electric field, right? So once you know the magnitude of electric field, again, you can use the relation that E into, basically your dielectric constant will be equal to your sigma, right? So that is your charge density. How do you find that numerical form? That's why you know you need the value of X, Y, and Z, where this equations will make sense. So suppose you want to find at this surface, there you have to use the equation for V equal to 0. Here, if you want to find at this surface, then you have to use the relation for V equal to 30, right? So that, okay. Is there a question? What's the book or material that you use now? Okay, so I think the normal theory, or you can say the concepts, I have just followed Griffiths, and I think some questions like this questions were typically taken from the last year's assignment that I got in the website. And some other questions that I generally solve, they are like from some question papers of, CSI or NET or some competitive exams. So I just choose some questions from there. And otherwise, I choose questions from last year's assignment. And mostly the theory comes from either Griffiths or Jackson or like some standard textbooks like that. Okay. So that means like for questions like this, which generally comes in your assignment, this is how you can try to solve the question. Do you have any particular question regarding this? If yes, you can ask me now. Okay. Because now we will, slightly change gear and talk about a little different thing. So about Laplace equation, do you have any question? If yes, please ask now. Later also you can ask, but you can ask now if you have anything. Okay, so let us go ahead. And now we will slightly, look into one of the applications of Laplace equation. Okay, so this, when we started with, we spoke about this behavior of, solutions of Laplace equation, which says that it has no maxima or minima, right? You'll see how this particular property of, solutions to Laplace equation actually led to this important theorem, which is called the uniqueness theorem. Okay. Now, what does this theorem tell us? So we would see that there is this very, useful method of images, okay, which will gradually come to. And that method of images actually tells us that if you are given a problem, okay, where you are given the potential, you know what is the potential at the surfaces, okay, and you are asked to find a potential somewhere inside the region that is enclosed by the surface. If that is the question. So in those kinds of question, it is seen that one can use this method of image charges that we will discuss. which makes the calculations much simpler. Okay. Now, this very idea of image charges actually came from this important theorem called the uniqueness theorem. What does this theorem tell us? So it tells us that the solution to Laplace equation in some volume V is uniquely determined if V is specified on the boundary surface S. So what it is telling you is that if you know the potential on the surface, if V is specified on the surface, the potential that is inside this volume enclosed by the surface, that is a unique value. Okay. So the solution to Laplace equation is a unique solution. Okay. So that means, suppose, you have some form of, potential that is given because of some charge distribution, Q1, Q2, Q3, anywhere, and you know the potential in this region, you know that the potential inside the volume is some unique quantity. So if you change the charge distributions here in this region in a way that the potential specified on the surface does not change, okay, you do all kinds of changes here, but that does not change the potential that you have on the surface enclosing the volume, then the potential inside in this volume will remain still the same. Okay. What is the proof of this theorem? So what this is telling you is that suppose let us consider that there are two solutions. We will prove that there is only one solution, but let us consider two solutions. So that means you have this relation. Now you say that V1 is also a solution, V2 is also a solution. So del square V1 is equal to 0 in this relation, in this region, and del square V2 is also equal to 0. So by the concept of linear superposition, that means if you take another function V3, which is equal to V1 minus V2, then V3 should also be a function of the Laplace equation, right? So del square V3 should also be 0. Now, we know the potential here, right? So if we know the potential here, basically, it tells us that on the surface, so somewhere here, so there V3 will again be V1 minus V2. So if on the surface V3 goes to 0, that is, like, V3 cannot have any maxima there, right? So if you're like, what do I mean is, so suppose you have V1 and V2 solutions here, and then V3 is also a solution, and it takes the value 0 on all boundaries. Why? Because V1 and V2 are equal at this points. Now, if V3 is 0 on the surface, that implies that V3 also has to be 0 inside. V3 has to be 0 everywhere. Because of that condition, that the solutions to Laplace equation does not allow any maxima or minima. So if your V3 is 0 on this surface, V3 is also 0 anywhere in the volume, which implies that V1 has to be equal to V2. So that means you have a unique solution. Okay. So we will use this uniqueness theorem. So what we will do in the coming, like when we talk about method of images, is that suppose in a question, some potential is specified, we would slightly change the charge distribution, keeping the potential on the surface constant, the same as before. So the boundary conditions do not change. Okay. We would mimic a new charge distribution, which would have similar boundary conditions. And that would imply that the solution would still be the same. Okay, and we would try to solve for that. So we'll solve for a simpler version of our problem, and that would give us the exact same value of potential as the value for the question given. Okay. There's also another uniqueness theorem which says that in a volume V surrounded by conductors with some specific charges rho. So if you have different conductors and you know the charge density on the different conductors, if that is specified, then the electric field is uniquely determined, okay, if the total charge on each conductor is given. So if you know the total charge on all the conductors, you basically know what is the electric field in this region. So that's another form of the uniqueness theorem. So now based on this uniqueness theorem, let us move to this idea of method of image charges. Okay. So let us start with this question where it says that you have a charge Q and then there is this surface which is at zero potential. Okay. The question asks, what is the potential in the region above the plane? So in this region, what is the potential? Right. Now, because of the presence of this, conducting surface that you have, because it's set to be equal to 0, the presence of this surface will have an effect here, right? Normally, we know what is the potential for a point charge. It just goes as Q by R, 1 by 4 pi epsilon 0 Q by R. That's for a normal point charge in free space. But here you have a boundary condition which says that in the xy plane you have this conducting plane which is set to zero potential. So because of the presence of this surface, obviously the potential here will be modified. You want to find the potential here, the net potential here, which has effect of this point charge as well as this conducting surface. Now if we have to think about, in terms of like physically, what will be happening? You have a conducting surface. So there will be free charges here. Because of the presence of this plus Q charge, there will be some induction of charges on this conducting surface, right? So a charge will be induced on the surface. Now this bound charge or induced charge will also affect the field and the potential that you have in this region, right? So it's not a very easy problem to solve. Why? Because you don't know how the charge distribution is, how the surface charge density will be. We still don't know that, right? We just know that the potential is set to 0 here. Now, what do? We mimic, we do a replica of this situation, but with a more simpler charge distribution, right? So what we do, we look at the boundary condition. We want to find the potential in this region. So what is the boundary condition given? The boundary condition is V is equal to 0 at Z equal to 0 because you have a conducting plate here, and V tends to 0 far away from the charge. So if you go very far, Z square plus Y square plus X square greater than D square, then the same boundary condition with a more simpler charge distribution, we would still get the same potential in this region, right? That's the uniqueness theorem. So what do? Now we bring in a minus Q charge at, equally opposite direction. Like if it is in D distance, you take it to minus D and put a minus Q charge, right? So what does this charge do? So if you now consider these two charges, plus Q and minus Q, because of the symmetry of the problem, this will also set the potential in the XY plane to go to 0, right? And again, very far from these charges, your potential will go to 0. So that means this charge, distribution also satisfies the same boundary conditions. So now by uniqueness theorem, it tells us that if we now try to use this to find a potential in this, region above the plane, that will be same as the potential for this condition. Now this condition is this charge distribution is a very simpler one. You just have 2 point charges. What is the potential anywhere in this plane? So if you take a point X, Y, and Z, you just take the distance from the individual point charges. So this is your expression of potential, right? So this expression of potential, which just involves these 2 point charges, is actually same as finding the potential for this condition where you have one charge and one conducting grounded plane. Okay. Now, if you are asked to find the charge, what is the charge density? Again, you use this relation. So you know the V, you have to find, del V del Z at Z equal to 0, which is this plane, and minus epsilon naught, this value will be the charge density on the conducting plane. So if you are asked what is the total induced charge, you can do sigma dA and do an integration. So you would see that you end up getting, so this Q will actually be equal to minus of this applied, initial charge Q. Suppose if you're asked what is the force, okay, so what is the force experienced by this charge? How do you find it? So it's nothing but trying to find the force because of the minus Q charge, right? So you can see how simpler the question has become, right? But you have to remember there's a one major difference between these two conditions. In the first case, this is at zero potential. So the work done is just involves bringing the Q charge. While in this case, the work done involves bringing two charges, one plus Q and one minus Q. So the work done for this case, given case, will be half of the work done for this condition. Okay. Other things would be same. Okay. Now you can do a similar thing in maybe, in the spherical coordinates. Like you can have a question like this, where it says that, you have a point charge Q and you have this sphere of radius R and the point charge at distance A. It says that the potential on the surface of the sphere is 0. Now, how do you find the potential outside the sphere? Okay, so anywhere here, how do you find the potential? So that means now we can again mimic this condition where we have something which sets the potential on this surface to be 0 and anywhere too far the potential goes to 0. If these two conditions are satisfied, and we have some simpler version of charge distribution that will still give us the same value of potential in this region, right? That's the uniqueness theorem. So again here, what you can do is you can basically bring in a charge, okay? So you can bring in a charge, some charge somewhere here inside the sphere, which you call Q prime, right? So see, this capital Q, small q, will normally have a potential on this surface, right? Now you have to bring in some charge Q prime, some image charge, which is an imaginary charge, basically like you are trying to mimic the condition. So you bring in some charge which would nullify the effect of this Q charge on the surface and set the potential on the surface to go to 0. Right. So basically, if you take a region like this, so you bring in some Q prime charge and the distance from Q to the point is R, and from Q prime to R, that the field point is R prime, you have to find Q prime such that this value goes to 0 at small r equal to capital R. So from there, you will be able to get a value of about what should be the value of the charge that you have to put in and where you have to put in, how far from this center, right? So you can try to, like, if you just use the condition that what should be the charge such that the net potential on the surface goes to 0, that will give you the relation of the values of Q prime and B. Okay. Now, once you know this, once you know what is the Q, what is B, basically now you have a very simpler expression, right? So you just have two charges. One is Q, another is Q prime, and the distance between them will be A minus B. Okay. So now you know if you are asked what is the force, you can just use this relation, which is much simpler than trying to find the effect of, all the bound charge on the surface on this Q and all of that. So this is how you can use image charges to solve different problems. Okay. And this is based on the uniqueness theorem. Now, you can also have questions where initially in the last question we had the V set to 0. Now you can be asked, you can be said that suppose, the V is set to V naught. How will the image charges change? Right? So initially in the last case, we had some Q prime somewhere here, okay, at a distance B, and this set the potential to 0. Now suppose it is said in the question that the potential is V naught. How do you manage for that? So now you have to basically have a, combination of charge which sets the potential on the spherical surface to V naught, and anywhere too far the potential goes to 0. This is your boundary condition. So what is the new change in the charge distribution that you have to do, right? So here you have to see that first, because of this, normally because of this Q charge, there'll be some induced charges somewhere here, right? All throughout this region. When you bring in the Q prime charge, like in the last question, that actually nullifies that effect and you have the potential going to zero. Now you have to bring in some other charge, Q double prime, something, somewhere, which will set the potential on the surface R equal to capital R to V naught. How can you do that? So basically what you can do is you can place a second charge Q double prime at the center of the sphere such that V naught is equal to 1 by 4 pi epsilon 0 Q double prime by R. So you know what V naught you want. That is already specified in your question. You know the radius of your sphere. So you basically know what charge to put at the center so that the potential here becomes V naught. So now you have three charges. One is Q, which was initially given. One was Q prime, which set the potential to zero first. And then you had another Q double prime, which set the potential to V naught. So these are the three charges that you have. Now, based on this three, now you have 3-point charges. So you can now use this to find all the values, right? What is the force of attraction between the point charge and the neutral conducting sphere? How do you find it? So basically, you have to find the force of attraction between Q, which is your given charge, and these two charges, Q and Q prime, right? So for the neutral sphere, because it's a neutral sphere, so total Q double prime plus Q should go to zero. That means Q double prime should be equal to minus Q, right? So if you use that, now you can just write an expression of forces due to point charges, right? Q double prime by A squared. So you have Q double prime here, right? Which is at a distance of A from the Q charge. So the force is just given as 1 by 4 pi epsilon 0 Q double prime by A square. And then you have a Q prime somewhere here, which is a distance of A minus B. So you have another force term, 1 by 4 pi epsilon 0 Q prime by A minus B whole square. So this is just finding forces for, unit like point charges, which is much simpler. So now you can just use this relation, and this is actually giving you what the point charge would experience from this neutral conducting sphere. So you are mimicking the potential given in the question to find potentials in much simpler way. Okay, so that's the usefulness of this method of images. Now there can be questions like this where you are said that two infinite, semi-infinite grounded conducting planes meet at right angle. So where is my pointer gone? So they meet at right angle. In the region between them, there is a point charge Q. Now we have to set up an image charge configuration and calculate the potential in this region. What charges do we need? Okay, and where they should be located. So any idea how to answer this question? Basically, these two surfaces are at zero potential. So whatever charge we bring in, whatever new charges we bring in, that should still maintain the potential along X and Y to be zero, right? That will help us mimic the given condition. So can you tell me how many charges should we bring in? Like how many image charges would be required? And where should we put it? Any idea? So if you have any doubt, please feel free to ask, okay? Any idea? Or anywhere you are stuck, suppose you're not able to follow, also tell in that case, okay? Or if you know the answer, you can also tell me then. So you know the Okay, so you know the potential here is 0 and here is also 0. So that means if we have to mimic the condition, what you can do is you can bring another minus q here. That will set the potential to 0 along x, right? And to mimic this condition, like so that the potential along y goes to 0, you can bring another minus q here. But you also have to remember when you bring in, so basically it is something like this, right? So if this is your q charge, you bring in a minus q so that the potential along this line goes to 0, like entire, this thing. Now, when you bring in the minus q here and you have a plus q here, you also want the potential here to be 0. Along y also it has to be 0, right? So for that, you have to bring, first of all, to balance this q, you have a minus q. Now also, so that, it remains 0 along x and y, you also have to bring another q here so that the effects of this charges cancel out, right? So this is the kind of, distribution of image charges that you have to do. This is making use of the symmetry of the problem, how the potential still remains 0 along x and y. Now, once you know how the charges are, then things are very easy, right? What is the force on q? So basically, you will have an effect from this charge, right, which will be along this direction. You'll also have an effect of force along this direction, and there'll be a q which will be a repulsive force. So basically, you'll have a force along this direction. So there'll be a net force that you have to find. So this is just force due to point charges again. So if you want to find the potential at some point, x, y, and z, it would be nothing but finding the effective distance from all the 4 charges and doing a summation of them, right? That is your expression of potential. How do you find the force? So how do you find the force? That is just by, doing this relation. So this is like, there'll be a force due to minus q, force due to q, and force due to minus q, and finding the net force. Now, how much work did it take to bring, this is again, how much work did it take to bring q in from infinity? So suppose here you are bringing 4 charges, right? But effectively here you just have to bring 1 charge. So the work done will actually be 1/4 of what work has been done in the case of the image charges. Okay. Now, suppose the planes meet at some angle other than 90. Would you still be able to solve the problem by method of images? If not, for what particular angles does the method work? Now, for this question, so suppose let us start with another example where you have the angle as 45, not 90, but 45, right? So again here, how do we do? So we have a plus charge. Suppose this is the charge to start with. To balance this, you put a minus here. Again, to balance this minus, again similarly to balance it along this plane, you have a minus here, which is 2. To balance the effect of 2, you put in a 4 here. To balance the effect of 1, you also have an effect of 3 here. Okay, again to balance the effect of 3, you bring in a 5. So you have to go on in a series so that the net effect along, so the net field here and the net field here should go to 0. So how do you balance it, right? So similarly, again, so that the field becomes 0 here, you have to have something here and here. So these are all the different bound charges, image charges that you have to bring in. Okay. So that means here it's possible. So even if you have 45-degree, you can actually have a combination of charges which satisfies your money. You can try to find the image configuration. Okay, so the method works. But does it always work, right? So in this case, first of all, a general relation would be this. So if the angle between the two surfaces is theta, suppose in the first case it was 90, you needed 3 image charges. While here, how many do you need? 1, 2, 3, 4, 5, 6, 7, right? So 45, 360 by 45, 8 minus 1, which is 7. So the basic, or you can say general relation of number of charges that are required for this kind of problem where theta is the angle between the two surfaces is given by this relation. Okay. Now, what happens when you have some another angle, right? Like 135. Okay, what happens then? So in this case, what happens is you start with this Q, right? So to balance this, you have a minus Q here. This is 1. Now, you also have to balance its effect along this line, right? The potential is also 0 along this line. If you extend it further, it's a line like this. So the potential also has to be balanced along this line. So that brings you a minus charge here. Now, once you put a minus charge here, you also have to balance it along X, right? So you bring a third charge plus Q here. But now it's a problem. Why? Because this third image charge has come within the region where you want to find the potential. You have to remember, you are trying to mimic a given condition. The given condition was that you have these two regions. Okay, you want to find the potential here, while where there is only one charge Q. So whatever combination of image charge you do, that cannot change the given condition, cannot add new charges in the region where you want to find the potential. You cannot do that, because if you add a new charge here, you are basically changing the question at hand, right? So that does not work. So you cannot do that. So the image charge should not come in the region where you are asked to find the potential. It has to be in the regions outside the surface, enclosing the volume. Okay. So as long as your charges are outside the region, it's fine. In this condition, in this case, for potentials to be set to 0, you want the potential to be 0 along this region and also along this line. You are bringing another third charge which is inside the region where you want to find the potential. So that does not work. Okay. So this is not good. This will not work. So this does not work for theta equal to 135. So that means the method of image charges for this kind of question, where you have two such conducting plates with an angle between them, it will not work for all angles. Okay. So for what angles will it work? So it will basically work for angles which are integer divisor of 180. Okay. So something like 180, 90, 60, 45, it will work for all of them, but it will not work for 135 or those kind of angles, because there you will be bringing charges in the region of interest, which is not possible, which is not correct. Okay. Is it clear? Okay. So now you can also have questions like this. So this is similar to what we were discussing, right? So you have a point, Q charge placed symmetrically at distance D from two perpendicular grounded plates. So V is 0 here and V is also 0 on this surface. Now the net force will be. So what will we do? We will try to replicate this situation with image charges. How will the image charges be? It will be like this, just as we discussed. So now we have 3-point charges. We want to find the net force. So this is a minus Q charge. It will pull it towards itself. So you'll have a F1. Again, F2 will pull it towards itself. So you have a F2 downwards along this line. And this is a positive charge. So it will repel and you'll have a net F3 in this direction. So now what is the net force, which will be an resultant of F1, F2, and F3, right? Typical problem, very simple one. So you have to find F1, which is equal to F2, is given as K Q square by 4D, because the distance between the two charges is given as 2D. Now, what is the distance between this two charge? It is root 2D, right? It's along the diagonal. So now you find the force due to the third charge. So it's given as Q square by 8D square. So now you find the resultant. So the resultant of F1 and F2 will be directed in this direction, right? Sorry. So basically it will be directed inwards, right? In this direction. And you have a F3 on the, which is opposite to it. So the resultant will be difference of the two. So this is what you end up getting, right? So this is your net force. So the entire problem where you had, in the original problem, you had surfaces like plane surfaces with some sigma, right? If you don't use the image charge, what you have to do? You have to see what is the Q on the surface. What would that like solve for Laplace equation, try to find the potential on the two surfaces. And once you know V, you find electric field from there, find the sigma from there, that is the bound charge, right? And then see the effect. So it's a, like, if you have to just solve based on this given charge distribution, that will be like a bit trickier than what we just did, right? This is much simpler, just working with image charges. Okay. Now there can also be questions like this where, so suppose here you have 2 point charges, plus 3q and minus q, placed at 2 different points. You have an infinite grounded conducting sheet in the xy plane. At a point, some z, where z is much greater than d, the electrostatic potential of this charge configuration would approximately be how much? That's the question. Okay, so this kind of questions generally come in, competitive exams and things like that. So what is the question at hand? You have a question like this, right? So if we have to replicate this, the xy surface, the xy plane is at zero potential. So basically now you can bring in two image charges. So for 3q, you have a minus 3q. For minus q, you have a q. So these are the now 4 point charges that you have, which mimics this given condition, right? Now, given this, you want to find that somewhere, 0, 0, z. So somewhere along this direction, some z, maybe somewhere here, where z is much greater than d. Okay, much greater than d. What is the electrostatic potential? So here, first we will look at, so this is at a much larger point, right? It is far from this. The entire charge distribution is here. We are looking at a point which is far from the entire charge distribution. So we should first look at what is the net charge of the combination. What is the net charge? 3q minus q minus 3q q. So the net charge goes to 0, right? So if we just look at our basic idea would be, so if you have some combination of charges and if you are very far from the charge distribution, the first order effect should come from considering this entire charge distribution as a point charge, right? But that effect will not be there here. Why? Because the net charge is 0. So now that means we have to look for the second order term. What is the second order term? The second order term is you have pairs of charges, right? Symmetrically placed pairs of charges. Basically, you have 3q minus 3q with a distance of 2d between them. You again have plus q and minus q with a distance of 4d between them, right? So now you can consider the charges in pairs. Okay, so two equal and opposite charges in a pair forms a dipole. So now we want to see the effect of the dipole at a very far distance. So the first order term will come from monopole, which is just looking at individual charges. So there the net effect will come from the summation of the charges. In this case, the summation goes to 0. So the first term is not there. So we will then look at the dipole term, that is the next order term, right? So now for dipoles, we have to find that what is the dipole moment for, suppose, this 3q pair. What is the dipole moment for this, plus q minus q pair? And one can also consider, dipole moments for this combinations, right? So basically, the monopole moment will go to 0 because the net charge is 0, but the dipole moment will be there. So how do we find the net dipole moment? Basically, we have to do what is the force, what is the charge, and how far it is from this point, right? What is the distance? Basically, q into d, right? That is your dipole moment. So you have 3q into d plus minus q into 2d. Again, you have minus 3q into d plus q into minus 2d, right? So you do all these combinations to find the dipole moment. Okay. Now, that means because the first term, that is the summation of the charges, have gone to 0, we want to now find. Okay, so this PPT, I think we will be uploading it, right? So I hope there's a Excel sheet that has been shared with like you guys. So in that Excel sheet, basically once we have this class, and then we upload the link to the video, and also the PPT PDF will be uploaded. So you can actually uh, get it from there. Is it okay? Yeah. So now this is your dipole moment. So now if you have a net dipole moment, what is the potential for a net dipole? So this is your net dipole for your question. Okay. Now the potential for a dipole is given by this relation. How do we get to this relation? So in later classes, we can talk about the multipole expansion. Basically, if you have some given charge combination, how the potential will be and what are the different moments, okay, the different terms, and how do they depend on R, and what is the common general form of the potential. So that comes in the multipole expansion, which we will discuss. But for now, we know that if you have a dipole with a dipole moment P, okay, and if it is at a distance R, then the potential is of this form. Okay. So now, because your charge distribution has a net dipole moment, we can basically try to use that here. So your P is given as 2qd, right? And then you have 4 pi epsilon 0 z square. Why? Because in our question, it is said that we are at a region where z is much, much greater than d. So basically, you can replace your r by z. So this will be your expression for an approximate value of dipole potential at the point asked, right? But in if you have to give a complete potential expression, then you have to look for multi-order terms as well and see how they turn out to be. So that multipole expansion will come up in the later classes, where we will look at a more complete description of potentials for charge distributions. Okay. So whenever you have a combination of charges like this, first see what is the net charge. So that will give you the monopole term. Then look at pairs and see what is the net dipole moment. Okay. So normally when you have two equal and opposite charges separated by a distance, that forms a dipole. So that means whenever you have a question like this, look for the net dipole moment, and that will give you an effective, value of approximate potential at a point. Okay. Now, okay. Now let us slightly now change gear and talk about Biot-Savart's law. So till now we have been talking about electrostatics, where we discussed about charges and charge distributions and what is the field, electric field, what is the electric potential. Okay, how do the medium properties affect what is the dielectric constant? Okay, how does it affect the electric displacement vector and all that. So we talked about electrostatics. Now you can also have magnetostatics, where you have constant magnetic fields. And steady currents are the sources of constant magnetic fields. Okay. So there comes this Biot-Savart's law, which tells us that if you have a region, some current carrying wire, where the current is given as I, okay, and you want to find the effect due to this current carrying wire, what is the field, magnetic field at a point, okay. So this is the general relation called the Biot-Savart's law, which tells us that at a distance r from this current carrying wire, we can actually take small line elements along the current carrying wire and do an integral of this form to find the net field. That is your Biot-Savart's law in general. Okay. Now, based on what do I say, the question at hand, basically, like based on the kind of current carrying element, how the element is, you have to choose your choose the line integral, choose the correct, what do I say? Um, Based on the question, you can choose the correct, reference frames. Okay, see what are the components that remain. Okay, which can make things simpler. So in many cases, you will have symmetry in the problem, where you can make use of the symmetry to see which component of the field actually remains. So you can try to find all that relations. So here it is said that find the magnetic field at a distance s. Sorry. So find the magnetic field at a distance s from a long straight wire carrying a steady current I. Okay. So here you take so suppose you have a long straight wire like this. Okay. So you take a small line element like dl. Okay. Try to find the distance r from here. Now in this case, you can define an angle alpha, and from here just by looking at, so this is alpha, this is 180 minus alpha, this is 90. So you have a relation between this angle theta and this angle alpha, right? So basically what you can say is dl sine alpha is equal to dl prime cos theta, where theta is the angle that it subtends at the field point. You want to find the field here. So what this line element subtends, the angle subtended here is given by theta. So now these are like all trigonometry that you are trying to do. Okay. And then from here you can find dl prime, which is basically taking the, like L prime is S tan theta, then take the ratio of the two and find an expression for dl prime. And then again look for what is the effective distance. Where is my cursor gone? Yeah. So what is the effective distance? Okay. So what is the perpendicular distance? What is this? L, this is L prime, this is S. So what is the value of R? Okay. So once you know all that, you can substitute it in the general form, right? So B is equal to mu 0 I by 4 pi. So here you can have a, so for a general wire of some length, you will have, just ignore this. So you will have two angles subtended at the two corners, right? So if this is your field point, you will have some theta 1 here and some theta 2 here. So you can do an integration from theta 1 to theta 2, where this is how it looks like. So basically this is just using Biot-Savart's law based on the question at hand, making use of trigonometries to find the line elements and the components. Okay. Trivial stuff, you can go through the derivation, but the main point is you get a form like this. Now here, if you have an infinite wire, what you can do, you can put theta 1 to minus pi by 2, theta 2 to pi by 2. And because the angle subtended at this point for an infinite wire, which goes all the way like this, the angle subtended will be 90, and from this end, it will be minus 90, right? So if you put that limit, you get an expression for B. So this is an interesting, important result, which tells us the field due to an infinite current carrying wire. Now, if this is the field for the current, later we will talk more about it. But once you know the field, if you are asked to find the magnetic intensity, so you remember B, like for now, you can just remember. So B is equal to mu or mu naught, whatever, the permeability into H. So H is called, just ignore my handwriting. Okay. So H, this is H. So H is called the intensity, magnetic intensity. So suppose you are, the current carrying conductor I is given, the distance from the conductor is given, you are asked to find the magnetic intensity. In that case, just ignore the permeability term. It would be I by 2 pi S. Okay, something like that. So you talk more about the relation between magnetic fields and intensities if required in the coming classes. But more importantly, you can now use Biot-Savart's law to find the field due to a current carrying infinite wire with current I at a distance S from the wire. Okay. So now using this, you can find all these kinds, and this is the more general form. So for some finite length of wire, this will be the relation that we'll be using. So you can have questions like this, where you have a current carrying wire along this square. You have to find the field at this point. How do you do it? So now you can consider four individual, line segments. Each line would subtend a 45-degree on the two ends, and then you have four such line elements, right? So basically, Z is equal to R, theta 1 equal to minus theta 2 equal to 45, and you have four sides. So first you find for one such side and then multiply by 4. Okay. You can also have questions like this, where you have this, semi-infinite, two such semi-infinite wires, and then a circular region here. So what you can do, you can use the superposition principle. So the field at point P will be a summation of the field due to, this region, again the field due to this region, and the field due to the like the semicircular region. Okay, so you can individually find the field due to such, semi infinite wire. Okay, so for the semi-infinite wire, what will it be? So one angle subtended at point P will be 0, other angle will be 90, right? So here you could see one was minus 90 to 90. That was for an infinite wire. For a semi-infinite wire, one of the angles will be 0. Okay, so in that way, you can try to find the effect of the net, um, you know, this infinite, semi-infinite wires, and then if you know the effect of a complete circle, the half of it will give you the effect of the semicircle, right? So to find the effect of a, like, half of the such a circular ring, you can try to find the field for such a small, circular loop. So here you have a circular loop at like you want to find the field at a some distance z of radius r. The loop radius is r, carrying current I. So basically you take a small line element along the loop, okay, and the distance from this small line element to the field point where you want to find the field is given as r. You can write r as, so if the perpendicular distance is z, this is capital R, so you know what r is, root over of r square plus z square, right? And then because of the symmetry in the problem, you would see that the horizontal components will cancel, so you'll only have the cos theta component, which is giving you the field along z, right? So you'll only have Bz, which will have the cos theta component. And here DL is perpendicular to R. Okay, this makes a 90-degree from with each other. So this simplifies your expression. And then you can do an integration. So when you do an integration, basically it's an integration over the circumference. So DL integration gives you 2 pi R. Right. So that gives you the general expression. This is a very important relation that one should remember, because many a times this will come very handy. So now for the question at hand, if z is 0, that is at the plane, at the center here, if you want to find, then you put z equal to 0. That gives you the expression of field because of a circular loop at the center. And then for a semicircle, it will be half of it. Okay. So basically now you have two half lines which are same as one infinite line. So this is the effect for this, for this and this section. And then for this section, for the semicircle, you have this value, right? So now the sum will be the net resultant. Okay, always remember the magnetic field as given by this relation. The magnetic field is perpendicular to the DL, that is the line element along the current carrying wire, and R, which is the distance between the field point and the current carrying element. Okay, it's perpendicular to both of them. Okay, so that will give you the direction. This will give you the direction of magnetic field. If you are asked to find the direction, look for what is the direction of your line element or current carrying wire. Suppose you have a current carrying wire along Z, right? So that means DL is along Z. If you are asked to find the point at some point here, which is along X, so then your R cap will be along X. So then it is an integration, like this cross product is along Z cross X. So that means the field should be along Y, right? Z cross X is along Y. So that will give you the direction of the magnetic field. Okay. So these are the different types of questions that I thought I'll discuss, right? So I think that's it. So thank you. So today we discussed about Biot-Savart's law, which talked about, magnetostatics. So basically now we are starting with magnetic fields. Till now we were talking about electrostatics. And in electrostatics, we discussed about this important concept of uniqueness theorem and image charges. And we did try to solve for potentials using Laplace equations, right? So that's about today's class. Thank you. Okay, so yeah, thank you.